All right, hello and welcome to another episode of Ether Roundtable. Tonight I'm going to be presenting on optics, and then we'll have a Q&A after. So we'll get right into it here. So you guys are all on the stream. You can all see. All right.
Yes, sir.
Well, I'm sharing the wrong window on what's it called? Second. Oh, there we go. Got it. All right, cool. Here we go. You guys, did it share the right window still?
It shows blank optic screen.
Once let me see. If that change. Will it? That change? Okay, we're good.
Yep.
Close
Yep.
enough. Fantastic. Okay, cool. Okay, we're gonna get into it now. Okay, so this is optics. This is curved visual space and how we see. So to give a little demonstration of what this means is we see in an azimuthal grid of vision, and this can best be expressed by watching this video. You can kind of see how it works, and then we'll break it down more in depth. So here we have what would be, the actual sun's location, and then we would have where you perceive it in your field of vision, right? Because you have a radius of vision, and this is what you see in. So everything you see in the sky will be projected into this dome relative to your position. Now I'll let this play out a little bit, and you can kind of see what happens when the observer moves locations and how it changes relative to their dome. Okay, so now they see it at that angle, right? Pretty straightforward stuff. And if you'll notice here, the familiarity of this dome of vision here has latitude, longitude lines that stretch out. So we'll get into that specifically on the next slide here. So a lot of people say the azimuthal grid of vision, that's nonsense. Is that something you just made up? That's ad hoc, right? Well, going back to the Royal Society when they were figuring out how to map the South, they actually pioneered the azimuthal grid of vision. So what we're looking at here is is a transit instrument, right? And what this bad boy does is you align it with the horizon, mark your site, flip it 180 degrees, mark that horizon, mark that site, and then you take your observations within that band. So they literally created this, and then made their observations accordingly in the what was that, like the 1800s? Actually, probably back even a little further than that. All right.
Yep.
So we'll get into how they tell us we see through Euclid. They say we see in Euclidean geometry, right? That the Euclidean geometry best describes how we see. So we'll skip over to the relevant postulates that we need here. So this will be postulate 4. All right angles are equal to one another, though a right angle measures exactly 90 degrees irrespective of their lengths of their arms. Hence, according to postulate 4, all right angles are equal to each other. This holds true for only right angle triangles, not acute or obtuse. Okay. And then this one right here, postulate 5, if two lines are intersected by a third in such a way that the sum of the interior angles of one side is less than the two right angles, then the two lines that intersect of that side will side if produced infinitely. So what he's saying here is if the sum of these angles is less than 180 degrees, these will converge. And if they're greater on the opposite side, they won't converge. All right, so the way that we actually see, I should have included some anyway. The way that we actually see is in curved visual space, and this is best expressed. I'll kind of give you a rundown of the definition of like what that is. So what is curved visual space? It's a geometric expression of optics that represents objects' form in physical location in three-dimensional space, meaning the object's physical location relative to where you perceive it based on optical curvature. The optical curvature will be presented as the mechanism that causes angular size to change relative to an object's size and distance away from you. Optical curvature and the dynamic angular scaling provided by this mechanism is how objects change size to fit into your 180-degree field of view. Distances in your field of view can be broken down into different types of optical compression: hyperbolic, ecliptic, with the near field and far field respectively. And then at an even farther, like at the far horizon, there's even a different type of curvature, right? So we'll get into a visual expression of that. So earlier when we were looking at the azimuthal grid, we saw that we see in latitude, longitude lines essentially, right? So in your near field, the optical compression rate is not going to be that much different than um, it's not going, you like the physical size relative to like its actual size and location isn't going to change much in your near field. Then when you get to the far field, you're going to start to see some changes, and we'll go over what those changes will look like towards the end of the slides. But the point is here is that as things get further away from you, they shrink in size, right? And then at the extreme distances near the horizon, the optical compression becomes logarithmic, and it's essentially um, anything that falls under that is outside of your outside of your resolvability. So that would be like the end of your azimuthal grid. So when an object um, exceeds that limit of your vision, of the radius of your vision, that's where you're gonna, that's where it's gonna disappear into curvature, right? But what kind of curvature? Is it optical curvature or is it physical Earth curvature? This has been the nature of of many debates over the past couple of years, and all of that's gonna kind of come to a head soon. Right. So, well, as we're looking into the history of curved visual space now, we'll go over some information that was put forward, or like some critiques that were put forward by Carl Rudolph Lundberg in 1947, who did a lot of work with curved visual space and really mapping that out. So let's see. We recognize that by binocular vision that we are surrounded by three-dimensional manifolds of objects. These objects, besides characteristics, qualities of color and brightness, form, and localization. So they have shape and they have a physical location in three-dimensional space. In the visual sense, thus are not only immediately aware of the distribution of the colors and brightness. So this isn't just about how bright something is with the color shade, but also of the facts that certain of these qualities are combined to unities, namely objects which have a definite geometrical form and a definite localization in three-dimensional space. We shall see, or we shall call this space visual space. Our problem is to investigate the geometrical character, i.e., the quantity and form of localization within this space. So he did a lot of research in mathematics in alley experiments, trying to map out how we see in curved visual space. So how to best represent mathematically how how we see an object in three-dimensional space, and based off of its size and location relative to us. Okay, so we'll go. He put forward some interesting critiques of Euclidean geometry that I found were interesting. So we'll go over those because those will be super relevant in Shane's presentation next week when he goes over the celestial sphere and sky optics. So the concept of visual space becomes clearer from the following consideration. We can coordinate the sensed points of a particular visual sensation to the points of three-dimensional geometrical manifold. This, of course, can be done in different ways. So he's talking about how to map it onto a coordinate system. We call the results of the coordination of the geometrical map of the visual sensation. Consider, for example, a coordination which is the basis of projection theory of binocular vision. A sensed point is represented by the intersection point of two projection lines which are drawn from two fixed points in Euclidean space. A base of points at the center of rotation of the eyes and the projection lines of the optical axis. We obtain this construction on a Euclidean map of the visual sensation. However, we cannot be sure that the map represents truly sensed qualities of the form and localization of the objects. This would be the case if the apparent distances or two sensed points were always proportional to the geometrical distances of the associated points on the Euclidean map. So he's saying, and we'll get into an experiment that goes over this specifically about the Euclidean predictions about depth perception at the horizon and how this optical compression really comes into play. So clearly, this is not true. Astronomical objects like the sun and moon are seen at at finite distances. Their sensed sizes is also finite, and there is no proportional astronomical dimension. Even the sky itself gives the impression of a dome of an infinite radius. Oh, no way, Lundberg, that's crazy. I wonder what Shane has to say about that next Tuesday. Everyone, make sure you tune into that because it's going to be a banger. It certainly does not introduce any special size sensations comparable to Euclidean infinity in its relation to the infinite Euclidean size or finite Euclidean size. These considerations indicate our actual problem. To find a coordinate of the sensed points of a visual sensation, 2 points of a geometrical manifold, such as the apparent distance of any two sense points, is always proportional to the geometric distance in correlated points. A coordination of this type is called a psychometric coordination. Whether or not such coordination is possible is a psychological problem which requires special consideration. The basic psychological facts, which we will discuss, will indicate, however, that in the case of visual sensation, a psychometric coordinate is possible. All right. So he's going over the difficulties of coming up with a way to map this all out. And he made some really interesting critiques about the Euclidean geometry and the relation to the sun here and the moon that we'll go over in a second. So what was he saying there? Well, Euclidean geometry assumes an infinite flat space where parallel lines never meet and the distances are consistent. In Euclidean geometry, objects at an infinite distance appear infinitely small. So if the sun is of infinite size, infinite distance, the way they consider it, you wouldn't even see it. It would just be a single parallel line to keep that form. But we actually see something that's 0.5 arc seconds angular size in the sky, and we see diverging and converging rays going to that focal point. So that's not really a possibility in Euclidean geometry. It's the exact opposite of the predictions. So just kind of go over that. So when we observe the astronomical objects like the sun or the moon, they appear near infinite size, not infinitely small, as Euclidean geometry predicts for an infinite distance. Additionally, their perceived sizes is not consistent with their actual astronomical dimensions. So they say that 0.5 arc second angular size sun we see in the sky is actually 860,000 kilometers or miles wide. So not real. And if that were the case, to produce these parallel lines that they do all of this math based off of, the sun would take up the entire sky. Right? It's pretty straightforward. So the discrepancy between the perceived size and actual distances of astronomical objects and their actual properties falsifies the Euclidean representation of visual space. It suggests that our perception of visual space is not purely Euclidean, but is influenced by additional factors of curvature. And something else that he pointed out here about yeah. So when he was talking about the sky as essentially a dome that converges at infinity, well, that's essentially what all these alley experiments are based off of, the ones that are in the dark. So we're going to get into those now. So these are the alley experiments. These are how they mapped out curved visual space. Is starting from the 1850s. They were getting into this. All right. So we have a diagram here of an alley experiment. So we'll look at the bottom half of the diagram here to kind of lay this out. So we have a parallel alley and a distance alley. So for the parallel alley, you're moving, let's say on the left-hand side, all these lights are lit up. And then we have single light sources here. And then your objective is to someone's going to like move it for you and then tell you when it's, when they hit the, when you think it's lined up. So basically you're moving along the y-axis to make sure that these are parallel, right? And then you have a distance one where it's the x-axis going up and down. So you're trying to align it on the x-axis essentially, while it's parallel. Okay. Now for Euclidean geometry, it predicts that the x and y plane will never intersect, right? Because of parallel lines and whatnot. Our visual perception shouldn't converge like that. There shouldn't be a convergence or any mixture of these planes. And let's see if I missed anything. Nope, that's it. Okay, so here's a diagram of what that intersection point looks like. Let's see, it was B and A intersect here at P, and they really should never do that. That's the whole point of that. So they determined off of that because of the intersection of these two planes that we actually see in curved visual space. And I'll read a little bit of this part right here. So this means for the alley problem, consider distance alley and the parallel alley both starting from a fixed point P in the mirror image Q. If the geometry is hyperbolic, then the distance alley lie outside of the parallel alley. And if the geometry is ecliptic, then the parallel alley lie outside the distance alley. And if the geometry is Euclidean, the parallel alleys and distance alleys are identical, right? They'll never intersect. They'll never be lying outside of one another to hit that intersection. So Bloomfield's data consisted of parallel alleys and distance alleys, different distances, blah, blah, blah. All right. So he basically determined off of that our visual sensation or spatial sensation is of hyperbolic geometry. So This is a falsification of Euclidean optics. Okay, let me see, check the notes. Got it. All right, so this is that experiment I was talking about earlier where they actually um, did some measurements based off of the Euclidean predictions in curved visual space. And this is a not to scale version of what they did, but basically these two things on tripods here, this arrow and this sphere would be far at the horizon, and then the bases would be covered in these weeds, so you wouldn't really have any secondary sources to judge, where they're located, right? You're just kind of looking at a floating this in the sky and this in the sky, right? At the horizon. And the objective here is to use this remote, and this person's not going to be anywhere near this. This is going to be far away, right? So, but anyway, this person's objective here is to use this remote control to turn this arrow so that it's aligned to the center of the sphere. And so this was about curved visual space and Euclidean geometry and the discrepancies there. Let's see, now that we have an understanding of curved visual space, let's review the measurement that shows the optical equivalence of the relationship that they call 8 inches per mile squared. All right, so if you have an observer here, and you have this at the horizon, you have your arrow at the horizon, your remote control arrow, and you have your target at the, opposite of that. You measure the angles between the observer and the pointer, and the observer and the target. So you got, what was it, lowercase theta and another theta or upsilon. So what you would do with that, the way that they give the derivation to convert this into the radius of your optics, right? Because they're going to turn this into a radius somehow. This spherical excess that's measured in this experiment, they're going to turn this into spherical excess. And then they're going to turn that into a length, and then they're going to turn that into the radius of our azimuthal grid of vision, and it's going to be completely equivalent to what they've derived as 8 inches per mile squared, based off of the celestial sphere. But that's for next week's presentation. So here's what the equation would look like. So the alpha equals 6 times. So the Gauss's theorem to produce to convert this into a length, right, is 6 times the angular excess minus 180, and that will give you your alpha or your angular excess. And then once you have that, you can turn that into a radius by doing 1 over the square of alpha, and that will give you an inversely proportional relationship to the radius. So they took those measurements, and they measured out curved visual space with a direct equivalence to how they present Earth curvature to us at 8 inches per mile squared, right? So the notion of intrinsic curvature was introduced by Carl Friedrich Gauss. This is from the paper where they did that experiment. So they were laying all this out, and they get into how they turn their measurements into spherical excess. So we're going to go over that whole process now. So the notion of intrinsic curvature was introduced by Carl Friedrich Gauss in a seminal paper dating back to 1837. Although the theory is arcane to psychophysicists, some of the consequences are relatively easy to grasp. Intrinsic curvature differs from extrinsic curvature. A flat piece of paper remains intrinsically flat when you roll it into a cylinder or a cone, although its extrinsic curvature may change. Intrinsic curvature is evident from certain non-Euclidean properties of figures. One example treated by Gauss concerns the sum of interior angles of a triangle made up of geodesics, the shortest arcs. Oh, no way. Euclidean straight lines. In the Euclidean plane, the sum of triangles would be 180 degrees. Any deviation is called angular excess. This reveals the intrinsic curvature of the space. Sorry, 1 second.
Pardon me.
Okay, sorry about that. In the Euclidean plane, the sum of any deviation reveals the intrinsic curvature. The excess is proportional to the area of the triangle. The excess per unit area, specific angular excess, is a measurement of the intrinsic curvature. Notice that it's a physical dimension, that its physical dimension is 1 over squared, thus the inverse of the square root, which gives you the absolute value, because it could be negative or whatever. But anyway, the specific angular excess has a dimension of length. So using the absolute value of their 1 over the square root method, they get their dimension of length. Gauss simply showed that it equals the radius in the simple case of a spherical surface. All right. So this is going to, so now they give a rendition of how to apply what Gauss put forward. So here's a very simple example. Consider a geographical triangle of Amsterdam, Boston, and Cape Town. They give the coordinates here. The triangle is 38,728, 38,700,000 kilometers squared. From Boston to Amsterdam, it is 5,600 or 5,568 kilometers. And they give the distance, like the distance of the length for the base of the triangle. And then, so according to Gauss, let's see, oh yeah, so this differs appreciably from the Euclidean. So they're saying that the sum of these angles presented on Earth, right, is appreciably different from 180 degrees, right? So it goes over 180 degrees. Thus, the Earth is significantly curved. Oh, no way. The specific spherical excess is 0.00507 seconds of arc kilometers squared. According to Gauss, this equals the curvature averaged over the triangle, and over the square root of this curvature equals 6,378 kilometers, which is the radius of the globe. So if you convert that to miles, it's 3959. So thus we obtained the radius of the Earth from the direction of the cities as seen from other areas on the triangle. Notice that the specific curvature is small. For instance, in excess of an equilateral triangle where the sides are 1 kilometer, the spherical excess is 0.002 seconds of arc. Locally, the Earth is quite flat. So this is something that you wouldn't perceive in your day-to-day optics. It's not something that could be measured over 1 kilometer. So 1 second. It's not something that can be measured over 1 kilometer. It's something that's inferred over great distances to make how you get there match, because all navigation is based off of the celestial sphere. So the arcs that they're deriving everything, all the curvature distances, it's all based off of an arc to a location based off of the celestial sphere. So it's not terrestrially perceivable at all. You can only measure it through corrections. Assuming that you're on a curved surface, and then how much you're deviating from that or from the sky. All right, so this is a graphic of what was just put forward. So we got Boston, Amsterdam, and Cape Town. This is their triangle here that they're saying gives an angular excess of 0.00507 kilometers squared. Then when you apply Gauss's theorem, you get your radius of 3959. All right, so a representation of what a triangle looks like in curved visual space is this. At different distances, right, you're going to get different levels of optical compression. Like, so the idea that you would see in a flat line, or that you would that these angles would all be 180 degrees, no, it's not the case at all. So they plotted this out from the experiment that they did with their three participants. All right. Let's see. So we were pointing out illusion when they applied it to visual space. Oh yeah, sorry. So without any more calculation, so this is just from the raw data too. This isn't even gaussing it up, right? This isn't even using the theorem to get the radius or anything. Without any more calculations, the raw data reveal that the optical space is ecliptic, positively curvature. In the near zone, it is hyperbolic, negatively curvature. In the far zone. Just from the raw data, from looking at it, they're like, it's pretty obvious. All right. And then they go on and say, does it curve? Okay. We have introduced a novel method to probe human optical space, namely that of extrinsic pointing. So they're talking about the methodology that they use to do their experiment. We use this method to address Lumberg's hypothesis that human optical space should be constant of negative curvature. So that was Lumberg's hypothesis, that the curvature rate was constant of negative, but that was later falsified. It's both. Near field's positive and the far field's negative. This hypothesis is clearly falsified by our data. The horizontal plane at eye height has an ecliptic curvature in the near zone and hyperbolic in the far one. A neutral parabolic distance is about an eye height.
Ooh.
The old neutral parabolic. What do you think about that?
So is he replacing Euclidean portion with neutral parabolic and still keeping super far field at hyperbolic?
What it sounds like, because you would essentially have to, right? Because you wouldn't have the linear portion of your vision wouldn't be linear. It would be like part of a curve.
Right? And he's calling so the neutral portion parabolic as in a function of x squared, as in, say, the curvature formula applied optically?
That's one to one
Hmm.
exactly. Yes.
Excellent.
Uh,
Okay, just want to make
m-
sure.
My question is where? Why is the word linear nowhere in here, ballers?
How dare you?
Yes, very good point.
Well, it actually is when they say at the beginning they mentioned that the Euclidean predictions were off by 30 degrees. So their
Oh,
linear their
wait.
linear their
So it is
linearity
in there.
their linearity
Oh,
was
that
off by
was
30 degrees.
that
Rest in
was in the
peace.
preface that we
Yeah.
didn't read, I don't think.
Yes. Correct.
Oh, okay.
Wow.
Okay. We'll talk about
Oops.
that 30 later, Shane. Maybe.
Yep.
Yep. Okay. So pictures of distance. Okay. Yeah. So we'll get into that here in a second. So we have
Lights.
Oops. Wrong video. Azimuthal grid. Okay. So we'll get into like a little diagram of what our azimuthal grid looks like. So if you take your left and right eye here at these 2 points, this one would be your left, this one would be your right. If you take a circle that vertically intersects your eye and then rotate both of those circles, you would get a sphere that intersects with latitude longitude lines that looks like this. That would make up a representation of your near and far field. So that's kind of how they describe it. That was something that Lundberg, that was how he described it. So he said that we see in a uniform sphere of illumination, right? And then within that is our radius of vision, is this thing. This is called the Vith-Mueller torus, and we'll get into that here in a second. So let's see. Lundberg's explanation: the distortion of the longitude lines represent where the different degrees of hyperbolic curvature are experienced by the observer based on the object's relative size and distance from them. As you get further away from the center of the observer, the lat long sections become more and more distorted as they both reconverge at the horizon. All right. So we'll get a little interactive diagram of the Vith-Mueller circle and how that curved visual space, how that compression rate changes relative to where you're focusing on uh sorry.
Are those eyeballs, those little circles at the bottom?
Yeah. Essentially, yeah.
Sorry, I was coughing for a second. Let's see here. So we're gonna watch a little diagram of what happens to this curved visual space latitude longitude system when you focus on objects that are in your near and far field. So we'll see what we're going to see here is dynamic angular scaling so that everything fits in your field of view.
I just got excited.
So this would be your left and right eye, and then the line intersecting out here would be like your point of focus, and then the 2 rings here would be your near and far field, and this would be the disparity in the types of curvature that are along those lines. Oops, that's the wrong button. Shoot. Okay, can you guys? Is it still playing the video now for you guys?
Yeah.
Okay,
Yeah.
cool. Okay. Sorry, I accidentally hit the wrong button. Okay, so I'll let that play out for a second. So right now he's focusing on something in the near field. You can see how that changes optically. Right. So just imagine that lat long system straightening out and stretching and converging so that everything fits proportional to your field of view, so that when you look at your cell phone you can see its size as it's represented truly, right? And then as it gets further away it gets smaller, right? Well, how does that happen? Well, that diagram is how that happens. So all right, why is it not? Oh, it's stuck on the video. 1 second. Okay, now we're back. Sorry about that. Okay, so again, this is just the representation of that again. Your left and right eye, and then the 2 spheres that rotate 360 degrees, creating your latitude longitude field of view. All right, close that.
Did it say this subsequent experiments? This has been proved over and over again. Is that what that page said?
So are your eyeballs, since you got 2 of them and you got an object that makes 3 points, are they basically like triangulating its position and then applying it to curved visual space?
Triangulation meaning that it's doing
Like
a
the
distance
projection.
measurement of
Yeah.
distance to derivation for each level. Yeah, sure, absolutely.
Yeah, there's proportionality between the perceived distance and the transition from elliptical to parabolic to hyperbolic.
Yes, dude nails it. Look at that. But yeah, look, so it says literally observed that a set of points are ranged horizontal and that this has been proved over and over again. Subsequent experiments have shown that this observation is substantially true. Not just regular true, substantially true. All right.
Substantially true. Yep. Let's see here. So, yep, on that. So this is Carl Friedrich Gauss, who was asked by his military. Oh no, I can't see that. Who was asked by his military to perform some geodesic measurings of mountaintops. So what he was doing is he was trying to get reciprocal zennies, right? But before they had the reciprocal zenny system, and he found that the angular excess found in between mountaintops is not much significantly different than zero. So
It's
you
nuts.
can make of that what you will, and we'll get it. And now we'll wrap up here with some demonstrations of what this looks like in practicality, right? So we have here lines on a road. Now, when the lines are close to you, you can see it to its proportional size of its actual length. And then as it gets further away from you, it stretches and compresses, and then until it finally just becomes a compression, right? Until you can't even really make out any details. And it's like, so is this, this is just in relation to that curved visual space, and as things get further into distance, how that optical scaling changes to fit everything in your field of view so that you can see all of this. And so you can see the whole horizon and everything and the clouds above. This is how everything fits proportional in our eyes. So some examples of this would be, if you look at the Blackpool Tower example, where they say that that the mountains couldn't be lower than the tower in the horizon unless the mountains were essentially reciprocating away due to Earth curvature. And it's like, well, no, there's an entire optical mechanism that does that one to one with what they say would be how far that mountain happens to be reciprocating. So, you know. All right, so here's another image of that that's a little more clear, so you get the actual first line there in its entirety, and then you can see the distance change or its apparent size change as it gets further away. You can see it more clearly there. So then here's another example. Here's a bridge setting. So this bridge goes out, and it gets smaller and smaller into the horizon, almost touching the water. But if you were to get into a boat, drive out there, well, it would be just as tall as where it looks right now. So all right, so now we're gonna watch flat Earths. We're gonna watch sunsets on a flat Earth, and we're gonna explain this mechanism with our curved visual space. This video is from Rakia Life. Shout out to Rakia Life. He's got some awesome sunset videos. So anyway, this one right here, you'll notice how the sun at the bottom here starts to diverge out, right? And it's like, what's causing that? Well, the sun is leaving your radius of vision, and as it leaves your radius of vision, you're going to start to see less and less of it, right? Because it's not a physical object. It's not we're not rotating away from it, and then the physical Earth curvature is obstructing it as we change positions relative to the sun, which would be essentially stationary in the sky. Not it's not what's happening. So I'll let this video play out, and then I'll explain, and then we'll watch a video from Zachary Zimbala do the exact same thing in a warehouse. He'll set a sun in a warehouse. What's up?
Maybe turn down the volume because
Yes.
you love to win.
Yes. Yep.
Yeah, that doesn't look like it's linearly scaling away to infinity, does it? That's weird. Looks like it's compressing or something.
Yeah, it's just optically compressing as it leaves your field of view, man. Your radius of vision. So skip ahead here. I don't think we need to watch the whole thing. We kind of get the idea. Then your boy boat goes out. Then you see, and now what's interesting here is we have these what are they called? What were these, buoys, I think?
Buoy towers or something?
Yeah, I can't remember specifically, but it's like all this is water right here. Right? And then we have this going on. So is the sun in the water? Like, no. No, this you can't resolve this, right, due to atmospheric conditions and optical compression, right? This is the exact type of scaling where, like in this area, where things would become unresolvable, where you would get where it just looks like there's no water here and there's just a sun here. It's all optical because you can't resolve it at that distance. So we'll go to the next slide here and we'll watch a sunset in a warehouse.
This one's awesome.
So if you recall back to what we just watched, we'll now watch Zach's video.
All right, folks. This is really neat. You got to check this out. The light is all the way on the ground as you
Fuck.
because it starts.
So to preface what he did here is he set up a flashlight in a warehouse right on the floor, and then he just walked away from it, had a camera, and took pictures of it at different distances. So that's what we're looking at here. Sorry about that. Forgot
in
to
the
give the preface.
background goes black, almost like a solar filter. And the objects converge as you saw. And now here is really cool because it starts setting like a sun almost. The bottom is getting cut off. And it gets more and more. This one was a little out of focus when I snapped it. But as you can see, as I kept going, there was more and more the bottom was getting cut off until eventually you just don't see the light anymore at all.
Are you saying that warehouse curved it? Oh, there's earth curve
Not
in there,
really,
right?
it's-
Dude,
They keep saying, show me a setting sun. Here you go. On a flat plane. And the light gets even less and less and less to where you barely see anything. And then finally the two mirroring images converge on each other. And there you go.
So there's the
sun is
Rayleigh
set.
criteria in effect, right? Resolution between 2 and 1 into 1.
Yep.
Beyond the limit of resolvability.
Up. All right. And then check out Shane's presentation tomorrow. So that's it for Curve Visual Space. Or check out Shane's presentation next Tuesday, where he'll be all of this will be applied to the celestial sphere and the sky and how they made maps, how they do navigation, how everything works on this plane that we live on, how they essentially used Curve Visual Space, our optics, to tell people that, well, the reason things are disappearing is because it's Earth curvature. And everyone just kind of went along with that. So that's over
Bro.
now.
You know what's wild about this? This would infer that, like, the fact that as you go south and go past the equator, you begin to lose view of Polaris. It just keeps going lower and lower and lower until you can't see it anymore, right? That would show that must mean that it's at an altitude at which at distance it actually, like, the angle is actually easily able to be messed with by a large margin, meaning it's actually very close. Like, Polaris has to be very close because of this effect.
Well, also, like you said before, to test this, right? If you apply a linear function to that, it wouldn't be resolvable. If you apply a logarithmic scale with approaching infinity, that would describe it more accurately. Like, hey, it's not there. It's there, but it's not resolvable, right? It's past your limit of resolvability. That's the best way to describe it.
Yeah, like with that warehouse demonstration at the end, I don't understand how people can argue against compression. It's like, what do they don't offer an alternative explanation, and there is no logical alternative explanation. Things that are, you know, parallel to each other in the distance are going to compress into each other. That's just the way it would work. And to bring it back to other things that you mentioned in your presentation, Alan, like a lot of things that you were talking about, was showing eyesight and two different eyes and the converging torus fields and how that gives us depth perception. But really, this would apply to a lot of this. Most of this would apply to all optics, which include photography, videography, because even though it's not exactly the same and we actually have less depth perception, we still would have we are still limited by the fact that we're taking in light from a single point within a 3D world, right? So no matter how you slice it, these are going to be rules that are going to be applied to your eyesight, to a camera. We have limited resolution, and that's why there is no, like the paper made very explicit. You can't just assume an infinite flat space with lines that don't intersect because, like it said in the paper, infinitely distant objects are going to appear infinitely small. Which, like, when you translate that to how we see, it means that the things that are farthest away are going to compress into each other, just like it showed there. And then actually, with the road image, I thought that was really cool because what that showed really well, if you look at those lines in the road and the way that they get smaller, the relationship of the lines that are the closest to the camera, and then you get further and further away from the camera, that relationship of the way that everything is shrinking and compressing is so clearly not linear. You just look at that relationship, like just use your eyesight, use your common sense. You can tell there's not a linear shrinking compressing relationship going on. It's a little bit more complicated than that. Things are compressing but not all at the same rate. But you don't even need to get that complicated with it, because like I said, there is no alternate explanation for convergence of parallel objects. Like you can't get away from it unless you're gonna be, omniscient somehow or something, and you can just visualize Euclidean space infinitely. Like and obviously that's just fantasy land. So yeah, fantastic presentation, Alan, and I hope everyone understood what was going on here. And if you have questions, please ask, because this is a massive topic. And for me personally, once I conceptually figured this out in my head about a year or so ago, there was no going back, right? Like I'm never going back to the globe at this point, because I understand now how compression works, how visual compression works, and that it's not only how it works, but that it's a necessity for optics. But yeah.
Dude, actually, if you take the angular resolution to its limit, right, and you try to figure it out and you factor in, a 6-foot observer height, and you get like the height of the horizon, and then you use that factorial to like backwards math all the, but you can derive the radius from your angular resolution limit from the part of the arc circle. Look at that. And then also you can describe the parabolic relationship of distance that he was talking about with the x squared function, right? The inches per mile squared. If you look down to there, that's the math that derives that parabolic expression into an actual expression of distance. And then using those two together, you can see how that backwards compatibly derives the radius from angular resolution and optics. So technically, 8 inches per mile squared was never a physical description, right? It could have been an optic description of the optical compression as it scales to infinity near the edge of your vision.
Yeah, so when I first came across this like curved visual space, I realized that it not only explains observations on a flat Earth, it literally falsifies the globe, because they assume Euclidean geometry and it's required.
They do, and they assume infinite linear distance scaling, and also is required.
Well, you know what I don't understand is when they make those triangles on a globe, and they talk about all this Euclidean stuff. One leg of that triangle is going to be cutting through the earth, or it's going to be painted as an arc. And technically, all of them are going to be arcs. All legs will be arcs. So it's like you don't have a triangle if you don't have 3 straight lines. You have 3 arcs. So if you try to do like the curvature formula, you can build a triangle, but the base of it has to cut through the earth. The actual distance traveled at the base is the arc you went over. So how do you even know what the true base of the triangle length is? It just doesn't make sense.
Don't they put themselves at the center of the earth exactly for that reason, though? Right?
No, I mean, if I want to shoot a triangle from me to you and then calculate the hypotenuse to like some mountain peak that you're standing on, right? But how do I know the base distance, like the base of the triangle from me to you? Because the base isn't a straight line. The other 2 are straight lines. The base is a curve. It's an arc. So if I assume that the distance of the arc is the distance of a straight line base, the straight line base is actually cutting through the earth. That means, like there's a difference in the path length of the straight line base versus the arc as a base.
Right. So let me ask you this, PZ. If you're pulling a curved arc from the sky and translating that to a linear plane, what would happen?
Yeah, so I mean, you would say that the sky is linear and the ground is curved.
I mean, if that were the opposite, right? That's what you'd have to say. But Just thinking, like, if you're pulling, triangulation from the sky and you're matching a celestial object, then that line you drew is not just a straight line. That's a curved arc because the sky is
Right.
curved, right? So
Right. Yeah. Same thing. Same problem. I wonder if you were to take a light wave and measure it and spin the little knob on your amplifier so that you did, adjusted the phase shift or the phase of it, right? And you, as you went around through the phase knob 180 degrees or even just the first 90 degrees, I wonder if any of the variables of that light that you're measuring when plotted on the graph would shift from elliptical to parabolic to hyperbolic. Like, I wonder if there's any kind of overlap between, the behavior of like frequency and oscillation with this proportional relationship with the what we see.
as usual, 4 to 5 steps ahead, man. Like, absolutely a good place to test it. Right? But it absolutely was limited to hyperbolic, elliptic, and parabolic. Does everyone understand like the differentiation? The near far and like extreme far field. So everywhere you see, like if you have bifocals, when you see like a four field, you'd be doing the geometry for Euclidean or linear, right? And just that the basic portion of your view. A little bit past that, in the far field, you have elliptic rather, where it goes in sort of an ellipsis, and you have the curved visual math applying to the geometry to get distance. And then right at the edge, where it compresses into nothing, you have hyperbolic, where it goes kind of extreme, and that's where you'd find also the other end of the logarithmic expression, where it would approach infinity but never reach it, right? Nope, just me.
Let's say again. Say again.
The way that they described it, because I snapped the screenshot there, is perfect. It does most of it, right? The bulk majority or the near field would be Euclidean, or what he would call parabolic, right? Because it's not really Euclidean. It's parabolic, which is, portion of it is linear, right? It goes linear for a little bit, and then it has a curve extending towards infinity. And then the far field of revision would best be described by elliptic geometry. So it has that curve and it has that calculation for distance that is not Euclidean. And then right at the edge of your horizon, that's the math that describes that is hyperbolic, where it goes kind of crazy and it approaches infinity.
It
That's
squeezes together into an infinitely dense point.
Yes. And I think this image is kind of crucial.
Well, yeah, because I mean, the sky in its curve, right? It's linear until 30 degrees.
There you go.
Yeah, so
Right. So
that
if you,
would bring it
yep,
back up to 30, like we said.
yep, we'll touch that next week. But this is kind of the crux of it, right? Determine that you don't linearly apply distance scaling forever. Appropriately apply the correct scaling based on the distance, which no one has correctly applied or figured out. And sort of the trick is what they've done is taken that function and let you use the linear portion and say, look, linear distance scales infinitely. And we can probably leave it there.
Wouldn't it mean though that if the way that you calculated it wasn't consistent across the whole length, that would mean that it's not actually all Euclidean space that they're claiming to measure because it transitions, from approximately linear to, parabolic, hyperbolic, or to hyperbolic one way and elliptical the other. So, I mean, you can't have that and still say it's just everything's Euclidean. It's all about trigonometry and straight lines, and it's not
Exactly.
consistent.
Exactly. Anybody else? Anybody else have ideas, comments, concerns, suggestions?
Not really, man. I would just say if anyone hasn't read the paper that we read last week, I highly recommend it. What is it? Measuring visual space, or what's the exact title?
The geometry of physical.
Direct measurement of curvature of visual space. I highly recommend it. We also read it live last Thursday. So if you don't want to actually read it, you want to listen to us reading it, you can go listen to that from last Thursday on Space Audits or Anti-Disinfo or on Aether Cosmology. But yeah, it's a pretty insane topic in my opinion. It's one of those things where, like Witsit was saying, it's really a globe debunk, and maybe one of the most easy and obvious ones that there are. And it's also just, I don't know, like once you figure it out, it just makes sense, and it's the type of thing where um helps to conceptualize what we see on a day-to-day basis. And I don't know if you're confused ever about flat Earth concepts of how we perceive the sky. There's like there's an insane number of factors there. It's a confluence of variables relating to refraction and our curved visual space, and us not knowing the exact nature of what's up there, and possible likely apparent positions of things that are not actually where they appear to be. And but once this is just one piece of that puzzle, but just in general, as far as looking out into the distance and making sense of that convergence that we see and what they would try to trick you into thinking is Earth curvature. Well, once you figure this out, you're like, well, you're calling it Earth curvature, but you're literally ignoring the rules of optics, just the simple matter of fact, logical, fact of the logical fact that we can't see forever. So
Right.
understanding this, having it on our tool belt is not only good for us to conceptualize our world, but also to answer people's questions. It was actually pretty funny. Like, the more time I spend with this, it's people ask me a question nowadays about something going over the curve, and it's like I just laugh in their face. Essentially, it's like, well, no, it's just you can't see forever, and there's a convergence. There's a compression point. Once you get too far, things
Right.
compress. You have a resolution issue. If you run a monitor on your computer screen, you can't just fit infinite amount of Google Chrome tabs on there or whatever. Like you have a certain amount of resolution of your monitor space. So it's the same thing with your eyesight. Same thing with the lens.
But you can see why they need people to believe that, right, Toby? For other things coming up, we need you to believe that you can see forever. We need you to believe that you think distance linearly scales forever.
Yeah, I mean, well, it should give someone pause, right? Like, why were we so stupid about this before? And it's like we even talked about it in, like, for me it was in middle school in art class. We talked about perspective. And that right there should be the end of the discussion. When people try to tell you about crap about boats going over the horizon and stuff, it's like, well, no, dude, we learned about this in middle school. There's a convergence, as things go into the distance. But yeah, you're exactly right, Shane. It gives me pause, the fact that this has been so absent from just simple discussions about space, about visual space, and about perception, and about Earth curvature, quote unquote. Because really, if the Earth was curving down and away from us in all directions, we should actually kind of have like a double. Ships should be going over the curvature like twice as fast as they are, or at like a different, like a higher rate. There we should be like in a sphere within a sphere, and so things would be even more spherical looking than they are actually.
Right. Dude, there's Gleam popping in. Gleam, I think, provided the seeds for what ended up in this presentation, right? Because he dropped 10 quotes on non-Euclidean 3D space that would pass to Witsit, pass to me, pass to a bunch of other people. And we kind of took those and ran with them, right? So we found sources of the sources, the typical thing you do when you're academically researching. If you find a paper that you like, right, you find all the sources that they use, you look up all those sources, you find more sources, you have nested sources, and then you do some research, right? So we took what Gleam gave us, I think, and set upon this whole path, unless I'm mistaken.
Yeah, well, I think there's also just an intuitive nature of it too. Like I remember when I first saw it, like I hadn't even really been thinking about optics that much when I first started investigating like flat Earth. And then I saw MC Toon's thing where he took an image and compressed it down into, like basically you take a horizontal line and then you compress it down, and then it imposes a curve on that, and he tried to use that as a proof of Earth curvature. And I was like, well, dude, you don't understand optics, because I can tell you just from having studied lenses that there's always going to be a curvature imposed, or just trying to shop for lenses for my camera, like it's photographer common sense that you don't use, you use different optical lengths for different field of views, because you don't want to impose a curvature. Essentially, that's the whole point. You don't want someone's nose to look gigantic because you use the wrong type of lens and got right up in their face, versus standing back and using a 55 millimeter lens. And so I understood that, and that was like, to me, got me thinking about all these things. And then it's like, and I started hearing inklings, probably coming from Gleam, that like, oh, what do you know? It's the exact same rate. Because I knew there had to be something like that. You start to realize just intuitively, you can't see forever. So it would have to kind of necessarily be some kind of a sphere that you would see out into a compression around you in, right?
Right. That's how I envision it. Seems to mathematically work perfectly. Yeah, but speaking of lateral image compression, did I have to play this video for the stream because it's hilarious? It's when you try to manufacture Earth curve from laterally compressing images and think that's real.
I hope you fuckwits aren't trying to manufacture Earth curve using lateral image compression again. I thought we already demonstrated how retarded that is. If you can compress a horizontal straight line to show curvature, then this process has zero merit. The people who keep bringing it up are the bottom rung of the intellectual hierarchy of globularity.
Sorry, I just had to throw that in there.
That
Since you
globularity
mentioned-
hierarchy. That's crazy.
Since they threw in that, this is how they used to measure curvature and prove curvature. It's like, yeah, we'll just nip that one in the butt.
Yeah, Toby, when you break it down, like from a photographer standpoint, it's like you said, oh, I don't want this person's nose to look all messed up because I'm using the wrong lens that's going to produce the wrong rate of curvature based on the distances and all that involved in the photo shoot. So it's like it's so intuitive, man, that like, man, they really did a number on us to get to make the narrative that we can see forever in straight lines and all this craziness. It's obvious,
Dude.
man. The sky converges into a dome. The dude said it in
So, like-
1942.
Yeah, like not to be a conspiracy theorist, right? But how long ago did they know this? And then decided to go along with the Euclidean thing, like for in perpetuity?
Yeah, it's odd, man. And I don't write off any possibility of premeditated, conspiracy of some kind to keep us in the dark about this. But I also think it's possible that like people just essentially are afraid to look for the truth. Like it's like almost like people keep their eyes closed willfully,
Yeah, there's something to that as well. Well, anybody else want to wrap it up? We got a nice even hour. That was perfect, dude. Short and sweet, concatenated, concise.
Global hierarchy, huh?
Globular
I
hierarchy.
wonder, man. I wonder where on the global hierarchy would fall things like gravitational anchor stones.
No, globular hierarchy is men only, right? They worship men. so-
People
Oh,
don't want the truth for the
dude.
most part. That's entirely correct, especially the liberals. This is the analogy: is don't confuse me with facts. I've already made up my mind.
That's pretty accurate.
What about the protractor boys, like the gravitational protractor boys? The Freemasons.
Yeah. Well, I'm gonna go ahead and wrap up my stream
some of them
if there's
aren't
no
as bad, I
more
would say.
subject matter related
The ones at
things.
the top
All
are
right, Alan.
definitely
Yep.
bad.
Cool. Yeah,
Thanks for
let's real thanks everyone for tuning in. And see you all next Tuesday for Shane's follow-up on this, which is being highly recommended, so don't miss it.
Yeah, we had to delay it. It was supposed to be tomorrow, but we don't want to rush it. It's going to be nice, polished, ready to go. So next week it is.
Yep. Awesome.
Cool.
Thanks for tuning in, and catch you guys on Thursday. So I don't think we have a subject set for Thursday. Anyone want to do you want to read Monera on Thursday, Toby?
Ooh, we should do that. Yeah, we should do that.
Awesome.
That's been on the back burner for a while. Yeah, let's do that.
It's been on the back burner far too long, dog. It's time to get Monera. All right.
Sounds great.
Awesome. So Thursday we're going to be reading Hector Monera's paper, and what he did is he left an interferometer running for 3 years, an orthogonal style setup. He left it running for 3 years and measured the same periodicity that Miller measured. So we're going to dive into that and look at his analysis of that. All right, cool. See you guys on that. And then Friday will be Flat Earth Fridays. So make sure you're tuned in for that. Peace.
Heck yeah. Take care, y'all.
Thanks for the effort, bro.